Let's do physics in 7 dimensions. Really, right at the beginning of the video. So starting with force, which is a measure of how hard you're basically pushing on something. But for our purposes, we need to quantify it a bit. So how would we quantify force? Well, when you have a cube like this with a mass of 1 kilogram and it's going forward at 1 meter per second, so for each second the position is changing by 1 meter, then if we apply force of 1 newton, we'll stop it after a second. Apply a force of 1 newton again and it's going back. So basically, for each newton we apply, the velocity is changing by 1 per second for each 1 kilogram. Or in other words, the force is equal to mass times acceleration. There, but still one thing we're missing, and that's the direction, because even though our cube is traveling at 1 meter per second right now, what if we apply a force right here? Well, now it's traveling at a square root of 2 meters per second in this direction? What? If we take 1 newton of force and add another newton of force, we get the square root of 2? Okay, so let's start simple, with force in 1 dimension. What would that mean? Well, we'd have a dot. Now for this dot we should specify some quantities, like its mass for example. We can set it to 1 for now, for the sake of simplicity. Then another thing would be its position. What position would basically mean in this case is just position. So set position to 5, the dot moves right here. Set it to -3 and goes right here. It's simple. Next we have simulation time, so when we start the simulation, as it goes on, we just add 1 to the time each second. That's how time works. Now that's for the basic quantities. Next we can add velocity. What does velocity mean? Well, it means that for each second that passes, we add the velocity to the position. So we set the velocity to 0.5 and then we add 0.5 to position each second, like this. Next we have acceleration. What acceleration would mean is the same thing as velocity, except for velocity. So instead of adding to position, we add it to velocity, like this. Now we got all the rules, we can talk about force, with the equation of F is equal to ma. Now this equation is pretty simple at this point. What basically means is that in our simulation, if we apply a force of 2 newtons for example, then this has to be equal, and since force isn't really affecting the mass, we can just move it on the other side and there. Now as long as we're applying a force, we can calculate the acceleration of our cube. So let's go over this again, because there is a lot of numbers on the screen right now. First of all, we have the basic ones, so the mass. Mass we just set, it's the mass of our dot, it locks and is unchangeable. Then we have the position. The more to the right, the higher the position. The more to the left, the lower the position. Simple. After that there is time. Time just slowly increases as our animation goes by, it only goes up, it's time. Then we have velocity, so velocity just means change in position over time. So if it's 2, we change our position by 2 meters per 1 second, each second. Next we have acceleration, which is the same exact thing, except for velocity. And then force is just following this equation, so modifies our acceleration accordingly. So now it's time for the example. So first, let's set our velocity to 1. See what happens. As you can see, our dot just moves right, because we add 1 to position each second. Then we reset the animation and let's see what happens if we set acceleration to 0.5. You can see that the dot is moving to the right once again, quicker and quicker. That's because acceleration changes the velocity, so velocity is going up this time. Now last, it's time for the force. So now, let's do the simulation again, except with a force equal to 1 newton for the first second of the simulation. Here's what it will look like. As you can see, the force is affecting our acceleration. But then when we stop applying the force, acceleration is no longer changing. We're left with a constant velocity. So this is what it looks like. Now that we have a full force classical model of physics, we can move on to force in 2 dimensions. So imagine that we have a circle and we push it in this direction with this force being applied over 1 second. Where will it end up after 2 seconds? Well, that's a solid question. How do we calculate that? Think about it this way. let's break the circle down into two one-dimensional dots. This one only going up and down, and this one only going left and right. Let's start the up and down. The up and down is getting pushed with 2 newtons, which means that this is what the simulation looks like. Simple enough. Right here we can see the same thing for left and right. Now, how could this help us get the full movement? Well, just take the up and down coordinate of the first circle and combine it with the left-right coordinate of the second circle. In this case, we'd refer to these as x and y. So combine a one-dimensional circle with a one-dimensional circle. That's why we don't have to do it in 2 dimensions, we can just do it in 1 dimension twice. Hold on, combine? What does that mean? Like, should we add them? Should we multiply them? Should we tetrate them? Well, it means just combine next to each other, like this. That's it. That's its position in 2 dimensions. And now we don't even have to keep all of those separate. We can actually merge all of them into a vector. That's what these are, vectors. In this case, 2-dimensional vector, since they represent 2 numbers. But how would we expand it to something like 3 dimensions? So a ball with a force like this acting on it. What now? 3 numbers? Yes, 3 numbers. You can see all simulations for all 3 of them. Now, that is one way to think about them, but this way we end up with a lot of numbers. So, isn't there like a way to simplify it? And the answer is yes. Think about this. This scenario might be in 3 dimensions, but what if we do this and move the camera? Now, it sure seems like a single dimension. All of these single values just lie on a random axis, this axis. So, how do we describe this axis using our 3 dimensions? Well, we can do it with a direction vector. So think about it this way. This entire simulation can be represented on a single line, so in a single dimension. That's because the ball is going in a straight line. So if you look at it this way, it sure seems like a single dimension. However, where is the single dimension? Or in other words, where is this ball going? At what angle? In what direction? Well, that's what we need our 3 other vectors to represent. That's why we can do all of the physics in a single dimension and then use a vector to represent it in 3 dimensions. And right here I would like to pause because this is the crucial moment of the video. What I'm basically saying, in order to do physics in 3 dimensions, we do it in the exact same way as in a single dimension, except 3 times. Physics in 3 dimensions is just physics in 1 dimension 3 times. But that's not over. You see, there is no actual reason for us to stop at 3 dimensions. So what would physics in 4 dimensions look like? Well, that's a bit hard to visualize since I'm using Blender for my 3D animations and Maya for 2D animations. I don't really have anything for 4D animations, but we don't need to visualize it to see what physics in 4 dimensions would look like. Here we have physics in 1 dimension, physics in 2 dimensions, physics in 3 dimensions, physics in 4 dimensions. We just add more numbers. And yeah, obviously there are some cases in which more dimensions really does complicate things, especially with graphics, but every now and then there are also some mathematical problems. But the point of this video is, if you hear someone brag about how many dimensions they're using or whatever, like, you know, some sort of douchebag saying, "Oh, I did physics in 7 dimensions," then that by itself is not incredible, because most of the time it really will be just normal physics, except with 7 numbers. Why is this video so long? That was actually my entire point. Oh right, I'm gonna teach you how matrices work. So matrices, they have a reputation for being confusing, which is actually pretty funny, and that's because they are actually trivially easy to explain if explained correctly. So first, let's start with an awful method of explaining, which is the one you've probably learned in school. This equation. Yeah, it's pretty bad, isn't it? It really is. For just a 2-dimensional matrix, you have 8 numbers which crisscross and sum together and whatnot. It's horrible. It's something that no one can possibly track. So allow me to show you a different method. When you have a vector like an arrow like this, it's made out of 3 different basis vectors rescaled. So we have an arrow with length 1, and length 1. Now we just multiply the arrows by their corresponding colored numbers. That's what a vector is. These three numbers into a single number. Now what about matrices? Well, imagine each of these colored arrows and realize that they are all vectors, and you can't get them off their axis. So now you can move them around, and all of these vectors would have their own coordinates, so the coordinates of the red arrow, for example. We can move it forward, backwards, left, right, or up and down. Green arrow, the exact same thing. And same with the blue arrow. There, now we have 9 numbers to represent these 3 vectors. 3 for the red arrow, 3 for the green arrow, 3 for the blue arrow. And that right there, my beloved interns, is the matrix. The coordinates of our 3 colored arrows. So moving on the x-axis rescales the red arrow. The y-axis, green arrow. Z-axis, blue arrow. That's what the matrix transformation is. We're moving the underlying of vectors. So when you see a matrix transform like this, now you should know what it means. And just to make sure that we're all on the same page, here is us moving the red arrow, the green arrow, the blue arrow, and then x coordinate, y coordinate, z coordinate. So here's the vector, and here's the transform vector. That's what matrices are, and that's how to matrix. The only logical next question after matrices would be... I believe I answered that question already, but I should still clarify it a bit, because the answer to what are vectors might not be as simple as you think and for reasons that you think. And that's because when it comes to vectors, there are actually 3 ways you can think about them. The physical way, the mathematical way, and the computational way. Most people get introduced to vectors with a physical way, which is a problem because physical way is really intuitive, but in the wrong way. Physical way means the arrow. So, for example, if you have a ball going 1 meter per second in this direction and 2 meters per second in this direction. Now, this is convenient because if we want to find out what it will be after a second, we just take these arrows and add them together. There, that's where a ball will be after a second. But where would it be after 2 seconds? Well, we just take our arrow and add another one. 3 seconds, add a third one, and so on. You can certainly see why this would be useful. But now let's jump to the opposite side of the spectrum, to the computational way to think about vectors, which is this. Just numbers. Now, what these numbers represent? Irrelevant. It doesn't matter. All you do is just operate on them. So when the computer receives 10 numbers like these and has to subtract 10 from each of them, it has no idea whether it's a video game where each player's health got damaged, an index of fruit in a supermarket with their shelf life, or some other hyper-specific number for which it just has to subtract 10. Computers have no idea, and because of that, we don't really care what the number does, what it's for even, or how many are there. That's why, even though doing physics in 7 dimensions might seem like a daunting task, for a computer, it doesn't matter. We just tell it to take all the numbers, square them, sum them, square root. That's it. And that way we can calculate the velocity of an object in 3 dimensions, 7 dimensions, or 20,000 dimensions. It doesn't matter. But then in the middle we have the math way to think about vectors, which just links them together. We have the matrix, which saw the way arrows behave, and then using that became a generalized method for matrices in higher dimensions. So basically, how could we rotate a cube like this? Well, we can describe all its points with vectors and then break them down into basis vectors multiplied, and then move these basis vectors around. There, our matrices again. Now we can take that method, describe it purely mathematically, and we no longer need the graphical arrows. Now we can take it to 9 dimensions to create a 9-dimensional vector and a 9-dimensional matrix and repeat the process. I want you to remember that you can just take a task, do it in 2 dimensions with arrows for example, generalize, and there, 9th dimension. Which would actually bring us to an interesting question. When we do physics in our universe, are we doing it in 3 dimensions or 4? Why is time a dimension? Well, it feels odd, doesn't it, to call space-time 4-dimensional, but it actually makes a lot of sense. If we imagine a ball like this, in this case this 3-dimensional space I have here is really convenient because the ball is also a 3-dimensional object, so if we wanted to specify its position we need 3 numbers, because 3 dimensions. So if we take this axis and use it to represent the first number, the more forward we are on the axis, the higher the number, the more backwards, the lower. Then this axis represents the second number, once again, same thing. And this for the third one. Now we can take the ball and we can see that its position is representing its position, which may seem dumb and obvious, and not because, well, it is, but I want you to really appreciate just how obvious it is, because it will be important to understand why time is a dimension. Now let's take our example and reduce it to 2 dimensions. So now our ball can only move on a plane, up and down, left and right. There's no third dimension, or at least there's no spatial third dimension, because in our example we'll also add time, which means that our ball can move on this axis, and will have its own animation, which will go on for 5 seconds. There, that's the animation. Now this is cool and all, but what if we wanted to visualize the entire animation all at once? Well, what we could do then is we could take the position of the ball in the first second and move it down, position of the ball in the second second and move it up, third second even higher, fourth second and fifth second. Now we can see that the position of each of these balls can be represented with 3 numbers: the x-coordinate, the y-coordinate and the time, which in this case would mean just up and down because we're representing time on the third axis. That's why time is dimension. It's because when you have a function dealing with the position of an object, you really often have to specify not only where it is, but also when it is. And right here you can see that these coordinates, when plugged into a function, are just numbers. That's it. That's why space-time is 4-dimensional. It's because if you want to describe the position of this ball, you really have to specify how far to the right it is, how far forward it is, how far up it is, and how far into the future it is. But all of those can be just specified with a single number, or in other words, represented with a single 4-dimensional vector. Okay, but then if they all can be represented with a number, then why is time clearly different? These are spatial, this is temporal. So why is time different? Well, there are a lot of reasons. The main one being that time behaves differently in most of our models. So if you have an object going forward, you can't really distinguish on which axis it's going. Is it X? Is it Y? Is it Z? Is it W? No idea. But what you can distinguish is the time axis, which will always be T, no matter what. So these 3 are interchangeable. This one is unique. And there, now you should understand almost everything when it comes to dimensions in physics. But there is still one last thing left to do. So, 4th dimension isn't real. In reality, it would be just one of the 4, and even though it may seem like a pedantic thing to mention, it is important because when people hear 4th dimension, they think of something which looks like this. No, in reality, if our universe really has 4 spatial dimensions, then there will be no difference between any of them. So if we have coordinates x, y, z, w for our dimensions, we really often think of x as left, right, y as forwards, backwards, z as up and down, and w being funky, but that's not quite the case. In reality, they are interchangeable, so x could be up and down, w could be left and right, z could be forwards, backwards, and y could be funky. So there is no 4th dimension, there's just one of the 4. We just say 4th dimension because it's more convenient to say. What if 4th dimension exists, but it's flat? You can imagine this easily with an analogy. Imagine a 3D space on which everything is flat. And here I mean perfectly mathematically flat, so not one molecule thick each molecule has a height of 0. So if everything is flat, then is this really 3-dimensional? Well, yes and no. Remember our 2 sides of the spectrum? Right here we would say no. Right here we would say yes. Because from our physical perspective, there is no way to move along the 3rd axis. What's the point of acknowledging it exists? From our computational perspective, however, this is just a 3-dimensional vector in which the 3rd dimension is always equal to 0. So, if the universe is flat, isn't even three-dimensional is a question, my dearest math audience, you'll have to answer for yourself. Which brings us to... does our universe really have only 3 spatial dimensions? Well, the answer seems to be yes. Very much yes. You see, dimensions have this cool property where they cannot really be easily faked. Here I've set up a scene in Blender and a flat sheet. Now, because of some really cool advanced Blender magic for which you should subscribe on YouTube and Patreon, I can move the camera up and only render things on the single sheet. And as you can see, as long as I'm moving in 2 dimensions, everything is fine. Until we start moving in the 3rd dimension. So if I move this sphere up right here in 2 dimensions, it will just appear out of nowhere, increase in scale, and then shrink into nothingness. The same way if we move the 4th dimensional sphere through a 3-dimensional space, then it would look something like this. And here's where the key part comes in, because when it comes to answering the question of how many spatial dimensions does our universe have, the answer really seems to be 3. That's because we haven't seen any anomalies like this. Now, there is also a possibility that everything is just flat in the 4th dimension, we can't really accelerate anything into it, but same difference. We might as well be talking about particles which interact with nothing and question if they are real. As far as physics is concerned, if it technically exists, but there is no way for us to interact with it in any way, it's not really real. So TLDR would be, we haven't detected any anomalies, so there is no evidence to support the claim that it exists. And so there, it's been quite a journey, a temporal one and a spatial one, a journey with vectors, matrices, physics, forces, but most importantly, if you count the time as part of physics, then you can create a vector describing how long each chapter of this video was, and if you do that, then congrats, you just did physics in 7 dimensions.